In this lecture, we're going to study the Blackboard architecture, which was invented a long time ago and is used to enable multiple solvers to collaborate to find the optimal solution for a problem. And we'll illustrate this, the use of the Blackboard architecture, with a method that's known as the Newton method. And the Newton method is a method where you evaluate the function that you are interested on finding the minimum for at a given point, and you compute the derivative of that function. Based on the value of the derivative, you decide the direction in which you want to move to do your next evaluation of the function. So the idea is that by computing the values of the derivative in around a point like this, I will start moving towards this local minimum here. And the way I ensure that I'll have convergence when I'm doing this movement is by decreasing the size of the step that I take as I execute the method. By doing that, the Newton method will find either the optimal solution or the optimal point, or a point that's very close to the optimal point with this simple computation of the derivative plus taking the steps. However, let's consider this function here. So if I have this function here, what will going to happen is that if I start exploring this function around the region of this local minimum here, the Newton method will get trapped in this local minimum because the Newton method can only find a minimum that is close because it keeps moving based on the values of the derivative. The Newton method is not likely to be able to move over to this global minimum here, given the way it works. So if you want to find the global minimum, we need to have something else besides the Newton method. Just to illustrate how it can get more complicated, let's consider that function that I have on the top of the slide now. With that function, finding the local minimum using a method such as the Newton method, or which is also known as the gradient descent method in machine learning, that would be quite difficult. So let's see how we can use architecture. Oh, and just to illustrate before we move on, let's look at some other examples that are more common in problems such as in machine learning, and many other optimization problems, where you may have very complex surfaces that might be quite high dimensional, and you need to find a minimum in that surface. So using local methods such as the Newton method only might make it impossible to find the global minimum that you're looking for. So we need something else besides these methods that specialize in the local minimum. And what we're going to propose here is that we use something called the Blackboard architecture. The idea of the Blackboard architecture is that you may have, it's called the Blackboard architecture because it's inspired on the idea that you'd have several students or several people sitting in a room, and each one of these people would be working on one algorithm to solve the problem individually and trying to find the best solution that they can for a while. So each one of these solvers will be solving the problem using the specialized method for a period of time. And then in this room there is a blackboard. And in the blackboard for the example of this single argument function, that's the two-dimensional case, what you're going to do, you have the value of x and the value of f of x printed on the board. So from time to time, each one of those solvers will check the blackboard. And if the blackboard has a solution that a value of f of x that's better than the one that the solver that's checking the blackboard has, then the solver will adopt the point that's in the blackboard and continue from that point. However, if the solver has a better solution, then the solver will will erase what's in the blackboard and will write over its own solution. And that's how the many solvers that are using the blackboard to exchange information will pass information about where the current solution or the best current solution is to each other. So the idea here is that I have a processor A that's executing the Newton method, so it is specialized on finding a local minima. And the other processor B will be a random search algorithm. A random search algorithm consists in simply randomly selecting a point in the x axis and evaluating the function at that point and comparing with the current minimum. If the new point is better than the current minimum, then it just replaces its current minimum. So the processor B has a local minimum that it's tracking as it's doing this random search. From time to time, both processors will stop processing and will check the blackboard. So let's say that I'm doing that and I'm implementing the blackboard architecture without having a lock. Let's see what happens. So let's suppose that I have the value x equal 35 and f of x equal 47. So it means that, at the point 35, the value of the function is 47. And that value has been written in the blackboard by one of those methods at some time in the past. And let's suppose that processor A, which is executing the Newton method, is currently its best evaluation of the function is at x equal 15 and the f of x is 56. And processor B has been doing random search and it has found that x equals 7 has an f of x equal 14. So processor B decides to read the blackboard. So it first reads the value of f of x to check whether the board has a better solution or not than the local solution. And so the board responds that f of x is 47. And before processor B does anything else, processor A then does the read of the board, and processor A also gets that the value is 47. And upon seeing that the value is 47, processor A says, well, 47 is better than 56. We are looking for a minimum here. Therefore, I know that the board has a better solution than the one that I have. I need to move to the solution that the board has. So it already got the value 47. So processor A will need to read the value of x next. But before processor A is able to read the value of x, processor B writes now the value of x because it knows that the board has a value that is larger than its local minimum, so it wants to post its new minimum. So it posts the value 7. And then processor A now reads the value of x, and processor A gets that the value of x is now 7, so it's going to make its local value of x equal 7. So what has happened here is that A now has read an inconsistent state. It's associating the value 7 with the value 47, which is incorrect. Because the next thing that happens is that processor B now writes the value 14, and the board becomes consistent again. So by having no synchronization, so doing the solution without any locks, it is possible that one of the solvers will get an inconsistent state. In this case, you can say, well, processor A, all that processor A needs is the value of x because it can compute the value of f of x, and that's correct. But this example, the simple example, is just trying to illustrate that when you have a state that you need to exchange that's more than a single data item, one of the problems of not using a lock is that you can end up with inconsistent states. So let's repeat now this interaction between processor A and processor B, but now we're going to be using a lock in our blackboard architecture. So now, besides x and f of x, the blackboard architecture also has a lock. And what we're going to do now, before a processor even reads the board, it will acquire the lock to ensure that it's the only processor that is accessing the board at that point. So it's going to do a load reserve of the memory position that contains the lock, and it will return the value of lock equals 0 in this case, indicating to processor B that nobody else is accessing the board. At the same time, processor A may do a load reserve into the lock to try to acquire the lock, and processor A may also receive the fact that the lock is freed, nobody is accessing the board. Of course, before accessing the board, processor B will do a start conditional into that lock position of the value of 1. In this case, nobody had written to the lock yet, so processor B will going to receive a value of 0, indicating that the start conditional has succeeded, and it can proceed then to read the board and update the board, knowing that no other processor will be accessing the board while it is reading and changing the board. Of course, when processor A tries to do a start conditional into the lock, it will going to receive a return that it is non-zero, indicating that the start conditional did not succeed. Therefore, it cannot proceed to read the board or update the board. So, as you can see, this is exactly the same mechanism that we saw when we look at the car and the truck on the road, trying to go through the narrow section of the road. So, and now the rest of the Blackboard architecture will work as you expected. Each one of the processors will be able to read the values in the board, update it, and then release the lock after it has completed the update. There are some related terms to synchronization that we need to be aware of. One of them is the idea of a critical section. A critical section is a shared resource. Usually it consists on a segment of code or a portion of code in your program that you need to ensure that the process that is executing that portion of the code is the only one executing that portion of the code. So you need to protect the code in the critical section with a lock. The other concepts, the concept of a race condition. A race condition occurs when you have multiple processors or multiple processes trying to access the resource at the same time without using any locks. So the result of a computation that has a race condition is unknown until the runtime. Starvation. The idea of starvation is that you may have, for example, 3 processors in the system, A, B, and C, and there is a shared resource that they need to access, and you could have that A gets access to the resource, and then B gets access to the resource, and then A gets access to the resource again, and then B, and C never gets access to the resource. We say that C is starved from resources, and that is where the concept of starvation comes from. And the last concept that we're going to address in this lecture is the concept of deadlock. Deadlock happens when you need to acquire multiple locks to access a shared resource. And in that case, if you're not very careful in writing your code, you could end up in a situation where processor A has acquired some of the locks, and processor B has acquired some of the locks. And neither of them will release the locks, and neither of them can make progress because they need locks that other processors are currently holding. In that situation, we say that we have a deadlock because there is no progress in the system because the locks are being held by multiple processors that still need other locks and are not releasing the locks that they have.